All right, so major idea number 2 for magnetic fields is, where do magnetic fields come from? Where do magnetic fields come from? The answer is they come from moving charged particles. And then you're like, well, wait a minute, Spaldo. Didn't you say that magnetic fields exert force on moving charged particles? Uh-huh. So magnetic fields exert force on moving charged particles, and they're also created by moving charged particles. So to put it real simply, what's magnetic fields really all about? Moving charged particles, okay? So here I have a circuit. Here I have a circuit, and I put a resistor over here. Here's a resistor just so we don't have a short circuit. So the current in this circuit is going around like this, right? You start at the battery, the current comes out of the battery, goes up like this, around like this, and then back down to the battery. Now look, I want to section off an area. I'm going to section off like this area right here, and we're going to look at what the magnetic field would be like around this wire. Because look, what is current in a wire? Current in a wire is nothing other than what? Like over here I have a circuit. This is for my regular class here. Look at, here's the circuit. What is moving through these wires? Electrons. Current in a wire is simply moving charged particles. That's all it is. So what will be present around a wire with current in it? A magnetic field, right? Hey, and even bar magnets. Like, you know, you guys take your bar magnet and you stick like photos of me on your fridge. Like, you just took a photo of me, right? You guys all have probably like candid action shots of me lecturing, like up here like this, and you like blow it up and stick it on your fridge. So anyway, you use a magnet, right? Now don't ask me to explain this in great detail, because I'll be honest with you, I really can't. But like, look, even a permanent magnet, what creates the magnetic field of a permanent magnet? Inside the permanent magnet, there are electrons, and those electrons are spinning, right? So it's ultimately charge motion. Charge motion is what creates all magnetic fields. What about the Earth's magnetic field? What's in the core of the Earth? A bunch of moving charged particles, right? And that's what creates the Earth's magnetic field, right? So what we're going to talk about here is if you have current in a wire. So if you have current running through a wire, there's going to be a magnetic field around the wire. Now I'm going to give you 3 choices, and I want to see how smart you are. 3 choices. The magnetic field around the wire is either going to be a triangle shape, a square, or a circle. A circle. Yeah, it wouldn't make much sense for a magnetic field to follow a triangular path. Like, right, it's a circle, okay? When you have current in a wire, the magnetic field is going to be a circular path around the wire, right? And this is the reason why you don't want to buy a house that's near power lines. I don't know if you ever heard about that. Like, if you know, sometimes homes are built like right next to these huge power lines that carry a tremendous amount of current. Well, if you buy one of those houses, what are you signing up for? You're going to be living in what? A big old magnetic field, far greater than the Earth's magnetic field, like a big magnetic field. So typically, you know, you want to buy your house away from power lines, you know, to avoid living in a perpetual magnetic field. Okay? So the magnetic field goes in a circular path. Now, there's 2 possibilities. The magnetic field is either going to be a circle going this way or a circle going the other way. The way you figure out which way it's going to go, can you guess? Right-hand rule number 2, which is called the curved hand rule. It's frequently called the curved hand rule. Right-hand rule number 1 is the flat hand rule. You keep your hand flat. Right-hand rule number 2, you curve your hand. So here's how you do right-hand rule number 2. It's super easy. What you do is you put your thumb in the direction of the current. So let's just say the current in this wire that I'm holding, let's say the current is going up the wire. So everybody put your hand out. Right hand out. Stick your thumb up. The current is up. The magnetic field is the direction that your forefingers curl of your right hand. So the magnetic field, so see my thumb is up, my forefingers are curling this way. So the magnetic field's going around like that. Does that make sense? Okay, now, you're going to be doing your work on paper, and paper is two-dimensional. So how are you going to show a circular magnetic field around a wire? So let's look at, I sectioned off a portion of the wire. The current's going through like this. So what you're not going to do is be like all creative and like, ooh, circle. That's not how you do it, right? The way you're going to do it, can anybody guess? X's and dots. Okay, so use right-hand rule for this segment of this wire. So the current is going that way, so stick your thumb in that direction. So what's the magnetic field doing in this region up here? It's going to be dots. It's coming out. I'll show you why in a second if you don't see it yet. Okay, now what's the magnetic field doing down here? It's X's, right? So you use X's and dots to show the magnetic field around a wire. So look, kids are like, what? So here's the wire, right? Put your thumb in the direction of the current. What's the magnetic field doing up here? Out. What's it doing down here? In. So the magnetic field's going like this. It's going in, out. It's going around like this. In, out, like that. You got it? So the way you show a circle is you use X's and dots, okay? Now, the equation for finding magnetic field at a distance from a wire. So if you go a distance r, so let's say you go a distance r from the wire, and you want to find out what the magnetic field is right there. The equation for finding magnetic field at a distance from a wire is mu naught I over 2 pi r. That's the equation, where mu naught's a constant. Mu naught, don't memorize it, I'll give it to you, 1.26 times 10 to the negative 6 Tesla meter over amp. That is a given, okay? So notice, if current gets bigger, what happens to magnetic field? It gets bigger. If R gets bigger, what happens to magnetic field? It gets smaller. The farther you are from the wire, the weaker the magnetic field. Okay? So this makes sense? Now, let's look at a problem real quickly. This is from your homework set. So, in this problem, we have two wires that are carrying current, and let's number the wires so we can talk about it. Let's say that this is wire number 1, and then this is wire number 2. Now what the problem wants us to do is calculate the magnetic field, the total magnetic field at the midpoint between the wires, which is like right there, and then we're going to go over here to this point and calculate the total magnetic field, and then we're going to go to this point and calculate the total magnetic field. All right, so how do you go about doing a problem like this? Well, the first thing you want to do is identify which way the magnetic field's going. So we're going to start at the midpoint between the wires. So this is current 1, this is current 2. All right, so focusing on the midpoint between the wires, which way is the magnetic field from wire number 1? So forget about wire number 2 for a moment. Just take wire number 2, forget about it for a second. Which way is the magnetic field at the midpoint between the wires from wire number 1? In. Now how did I figure that out? Right-hand rule number 2, right? So you stick your forefingers, watch, put your forefingers in the direction of the current. What are my forefingers doing at the midpoint? Going in, okay? And I labeled it B1 for magnetic field 1, from wire 1. Okay, now, wire number 2. What is the magnetic field from wire number 2 doing at this midpoint? It's also going in, right? It's like this. Put your thumb in the direction of the current. What are my four fingers doing at the midpoint? Going in, right? So are these magnetic fields going to cancel each other or add to each other? They're going to add to each other. All right, so then what we do is we use the equation. B equals mu naught I over 2 pi r. Mu naught is a constant, right? Okay, so then you calculate what's B1, what's B2, and then add them together, and then the answer will be into the page, right? So the answer to question A is going to be something Tesla into the page. Okay, now let's just do part B, and that'll be it. So part B wants us to focus at point 1. So now we're focusing over here, right? We're in this region right here. Okay, so what's the magnetic field from wire number 1 doing? So forget about wire number 2. Forget about wire number 2 for a minute. What's the magnetic field from wire number 1 doing? Going in. So that's B1. What's the magnetic field from wire number 2 doing? Out. Now look, before you do any calculations, you know which magnetic field's stronger. Which of these magnetic fields is going to be the stronger one? 2. This is going to be stronger. This has to be weaker. How do I know that? Well, because the currents are the same. So look at this equation. The currents are the same, but what's the advantage of wire 2? It's closer, so it's going to be a stronger magnetic field, right? So the way you do this problem is you calculate, calculate B1, calculate B2. B2 is going to win, which means the answer here is going to be something Tesla out of the page. How do I know it has to be out of the page? Because B1 is strong. I'm sorry, B2 is stronger. Okay?